Hello and welcome to this talk on production, and it's going to be focused on the use of that within stream ecology. One of the reasons that I've actually included a talk like this within a course on stream ecology is not because I expect everyone here to be enamored by modeling, but because I think it's so important to think about how we understand natural systems. And one of the ways we go about doing that is we try to understand them through mathematics. This is a common theme that we see in biology and ecology, and so I really want to stress the importance of using that tool to try to understand what I am trying to convey to you. So a lot of times I've told you information, but much of the information that we understand about the ecology of these systems is built from mathematical models that help us try to understand what's actually going on out there. So I understand that, again, that many of you are maybe not as interested in this, but I think it's so fundamental that to avoid it or to not include it in a upper division course would be unfair to you. All right, so what I would like you to do at the end of this lecture is be able to understand how material flows through systems and how we might track that. All right, so on the picture on the left, there's a caddisfly eating some material, and we would like to know how that material is flowing through the system, through that caddisfly, maybe into fish. But we have to go about measuring it in some way or maybe modeling it in some way because we can't actually literally watch each caddisfly. We're going to identify the strengths and weaknesses of this type of approach. You'll see some as we go forward. And I would like you to be able to do the simple calculations here. It's mostly subtraction and multiplication, just bookkeeping, in fact. So what is production? Well, production is a formation of living mass. The picture on the right is a good example of that. These fish start off as small, and at some point they get larger, and as they get larger, they put on more and more mass, and that mass has to come from materials that they're consuming. And so theoretically, we should be able to keep track of where all that mass is coming from and ultimately where it's going to end up, and we should be able to keep tabs on how that mass is being acquired. You can do that for primary producers. You can call that net primary production, or primary production is really what I should say, because it encompasses a couple different kinds. But you can keep track of how much, say, plant biomass is being generated. That's really important for a variety of reasons. You can also do this for organisms, right? There's no reason why you couldn't apply the same type of modeling to other organisms, and that's secondary. Occasionally we might call that tertiary or quaternary production, but usually we just think of that as secondary production, at least within the context we're going to understand it here. That seems a little tedious, but one of the exciting factors about food webs is that they're extremely limited in length. And so we don't have an infinite number of things eating other things. We have things eating other things up until we reach about maybe 3 or 4 levels, and then it really starts to slow down. And you can see here that food chain length is very tightly associated with the ecosystem size. Okay, so you end up having much shorter food chains as you get into smaller and smaller ecosystems. So if you've ever wondered why the ocean has such a long and complex food chain, well, it turns out the volume is enormous, so it's capable of having very, very long and complex food webs. Okay, so back up if you don't understand what I'm talking about. I meant something about trophic levels and things eating at those trophic levels. Well, you might think of this as another model, in fact, of the world. So we might think of the world divided into the steps by which materials get their food. So for instance, primary producers make their own food. That's the first trophic level. But something that eats a primary producer, we would call that a herbivore, right? And that's the second trophic level, okay? Something that eats an herbivore, right? That's a predator or a carnivore. That'd be your third trophic level. And then something very, very large that might eat those carnivores would be your fourth trophic level. Now we're making a number of really important assumptions here. Organisms eat in a sort of linear fashion, right? They can only eat one trophic level below them, and we know that's not the case. But it turns out that this conceptual model of how ecosystems are structured to some degree appears to be a relatively useful and robust way to look at the world. All right. This is very cool because it provides a simple way to understand and describe the world we live in, even though we know it's wrong. it still provides a universal way that we can describe ecosystems, and stream ecology certainly is no exception to that. So let's imagine we just did some simple bookkeeping. We're going to assume that trophic levels are real, and then we might ask how many levels or how many individuals are at a trophic level, or how many of a species are present within a system, and we're going to count every single one of them. And what if we then went and weighed them all, right? So we would need just a couple of things to sort of keep track of organisms in a system. How many of those animals were there at a trophic level, or that were a species that are present? How much they all weigh, and we need to do this at a couple of different time periods, right? It doesn't help you to know your bank account once. You need to check on it occasionally to make sure that you don't deplete it. And in the same way, we're going to need to understand how this is going to change through time in a stream. So we're going to need to measure this over time in a stream. And actually, you do this all the time, right? If you have ever been on anything like a diet, or you're even remotely interested in keeping track of how many calories you're eating, you are focused on, okay, how many calories are coming in, right? Your bookkeeping at certain times, usually at meals, right? And then you add them, you sum them up across the day to get the total number of calories which you've consumed. And you make some assumptions about that. One, that the labeling on the outside of the package is exactly 100% right. Two, that every calorie that enters your body is fully consumed, right? There's no loss of material. And three, that you're not missing any calories, that you are doing a good job of keeping track of every single incoming calorie, right? And you know that many of those rules are violated, and yet if you've ever been on a diet and you've kept track of calories, you will also understand that even though those things may be violated, they're not violated enough to prevent you from using that as a tool to help you lose weight, right? So it's wrong, but it's helpfully wrong, okay? Because it's very much in the right direction. Actually, this kind of keeping track of calories moving around in organisms was started by an ecologist called Odom. Turns out that I am a academic grandchild of Odom, and that my advisor was a student of Odom, and now I am a student of hers. I'm not very farly separated from Odom. Odom died more recently, say in the last 20 years, I believe. But he and his brother, also another Odom, were very important to ecological study. And if we keep track of how much material is moving around in a system, so let's move that idea about, well, let's keep track of things moving around in us to, let's make it bigger. Moving around in a system. Maybe I want to know how many calories it takes to raise hogs. And if I want to know how many calories it costs to raise a hog, that's because I want to know how much it's going to cost me to raise hogs, right? Where do I make profit on my hogs? Where can I increase profit by reducing the number of calories I need per pound of flesh that I sell, right? So that's really useful stuff. The idea that we can make these models that allow us to track energy in and around the system. And this is actually the kind of thing that he made. He just made some very simple assumptions. You could keep track of everything going in, and they were related to each other, and there was some processing that went on, and then there was some of that material came out. And you could use this with money. So Odom thought about this with money, but you could also use it, sorry, not with money, with energy, but he also pointed out that you could do this with money if you had some sort of conversion, right? If you know that you can make 1,000 pounds of pig flesh with 10,000 pounds of incoming food, and you know the conversion of pig flesh to dollar amount, you can estimate how much money is coming out of that system, right? So that's very useful. And then there's some loss to waste, right? You may be able to raise 1,000 pounds of pig, but after butchering, you may only get maybe let's say 600 or 700 pounds that are sellable. Maybe the other is material you can't sell, or it is of low quality so that it is effectively a cost to you to get rid of, right? So that's very useful in that sense. And again, we can do this exact same kind of bookkeeping stuff with stream organisms. So I don't want you to think that what I'm presenting to you is so unusual that you haven't done this before. What I want you to convince you is that these type of systems are all around you all the time, whether you acknowledge it or not. And we're just going to use it to understand something about the food web and streams. Now, timing does matter for this, okay? And again, I'm returning again to that pig farm. If you wanted to keep track of how these pigs were growing, you'd want to know how fast they were growing. At certain times, they'd be growing really fast, right? And they'd need a lot of food. And at other times when they're small, they would be growing quickly, but they're not very big yet. And so their total weight would be going up very slowly. There must be some optimum time when they're no longer growing that much, but they're really big and therefore worth butchering. You don't want to butcher nothing but piglings, right? Because those guys are going to be relatively expensive to make, and they're not going to have that much meat on them. And so if you're going to sell those, then you're going to need to sell those at a premium price. And so there's not that much demand for it. On the other hand, the meat that you would get from a large adult pig, that may be too long, right? It takes years to raise an animal to adulthood. Do you really want to do that? Or do you want it as a juvenile animal where, yeah, okay, it may not quite be an adult yet, but why do you care? All right, you're not trying to breed that animal. You're trying to use that animal for food. So what we're going to do is keep track of time as well as we go out into these streams. Here I'm making not a real stream, unfortunately, but we're going to actually look at a stream through time mathematically. And when we do that, we should see that production will go up and it will start to level off at some point. As we say in life, only two things are certain, death and taxes. And if you're a snail or any other animal, taxes in that case would be the removal of material from your body through things like respiration and feces. You got to pay to stay here, but ultimately you'll end up dead, sadly. Sorry. Death is really important for most organisms. There are some organisms which are immortal. Those organisms are things like bacteria, maybe a virus, because it's not really living, though. It's hard to classify in that way, although presumably a virus that sat in a cabinet for 100 years would still be, quote, alive by some definition if it reinfected something. Anyway, food that comes into an organism has to be converted to an organism's biomass. And as a result of that, because the universe requires us to pay a tax on that the second law of thermodynamics exists, aka that there's entropy is always increasing, or I should say that no energy transfer is 100% efficient. No matter what you do, you simply cannot make it 100% efficient. That is a universal law that we deal with. Then you have to pay some amount of energy out to use that energy that you've taken in. So there's losses to that. In addition to that, there's all sorts of stuff trying to eat you all the time when you're in a stream. So even if you do manage to put biomass on, a lot of you in the process of putting that biomass on are going to get eaten. And that seems sort of obvious when you think about it. If a mayfly is laying hundreds of eggs, then only 2 of those individuals have to survive from a female mayfly for the population to remain steady. And that means that the vast majority of eggs at some point, whether they're eaten as an egg or eaten as a nymph, are going to be eaten before they reproduce. Populations, I know in the Matrix they talk about this as a virus thing, but populations of all kind of biology grow exponentially, which is to say that they grow following this type of curve, which is a small number of things can make huge numbers of things because they follow exponential growth. And Darwin actually even pointed this out that elephants do this as well. And if they were given enough time, right, you can do some back of the envelope calculation and say, okay, how long does it take an elephant to reproduce? How often does it reproduce? How long does it live? Let's assume that all of those individuals survived and then they themselves started to reproduce. Well, in a few thousand years, the earth would literally be coated in elephants like a delicious cake icing. And that cake icing would be doubling in thickness every, I don't know how, every many few years, but it would increase very, very rapidly. And obviously that doesn't happen, right? Because the vast majority of elephants that are produced die. So in fact, the vast majority of individuals of any species die before they ever reproduce. And that is true in human populations. Prior to the modernization of medicine, humans produced many more offspring than generally survived. So they may have 4, 5, 6, 7, 8, 9, 10 offspring. But unfortunately, in general, only 2 of those individuals actually survived to reproduce. So those numbers are sort of staggering, right? Now that has changed since the advent of modern medicine, but in response to that, parents have often reduced the number of offspring that they have. So actually the total number of offspring produced in developed nations is actually net negative without the without the addition of immigration, because many people choose to have very few offspring when they know that they can control mortality rates very closely. So this exponential growth, which is really important for all biological populations, is going to be really important for us too. Not only can your population size grow exponentially, but your total volume will grow exponentially as well, because that volume, as you pack on biomass, is going to go up very, very substantially. So it's also going to look very much like this. That is assuming that populations also grew. Now, of course, many of your individuals are actually going to get eaten, but their volume will substantially increase. So there's going to be some period at which the amount of biomass a group is putting on is going to outpace or maybe eclipse the rate at which they're being eaten. So if you combine those two things together, you'll get something like this. You'll see a density curve that's inverted to the one you just saw because animals are getting eaten all the time, right? So actually the opposite's true. There's usually a big burst of animals on the scene through things like eggs or small offspring. And then over the course of the year, the vast majority of those individuals get eaten until, again, there's a big burst of individuals onto the scene. In comparison, the mass is going to increase exponentially up to a point where they reach probably close to a maximum size, and then it's going to start to level off, and that's what you see in this case as well. So the number of individuals is going to change pretty substantially through the year. And if we measure it at lots of different times, we can call the difference between two times delta n, which is the difference in population through time. And we can call the difference between weights at times delta W, which would be the difference in weight. Whenever you see that big triangle, that means delta, and it means change in. So change in weight, change in n, which is usually referred to as population. Okay. So this is going to be very simple then to keep track of all these things. We just need to keep track of what's going on in each little section between our sampling dates for both the number of organisms in the environment and the weight of those organisms in the environment. Effectively, we're doing something very much like this, which is estimating area underneath curves, because we're going to know something about the distance on the x-axis, and we're going to know something about the height on the y-axis. So that's a rectangle, a lot of rectangles. And we're going to measure the area under these curves by putting a bunch of rectangles next to each other. And the number of time periods you have, the finer the fit will be to that curve. So the better estimation you will have of that curve's area. The more coarse the time period is, or the more infrequent, I should say, the time period is, the more coarse your estimation of the area under the curve. But again, it really depends on what you're asking. Do you really need ultra fine detail like you see on the right, where the sampling periods are incredibly tiny in a sense? Or would you want something on the left where you have much broader sampling periods? Now, I know that this is not exactly the same type of curve you saw there, but this is frequently the type of curve that people expect to see, and that they often talk about sampling under the curve, so I wanted to show it here. The principle is identical, regardless of whether the curve doesn't have a descending limb or it has 50 descending limbs. It doesn't matter. You're putting little tiny rectangles underneath it. You're measuring across on the x, measuring up on the y, and then you add all those together for however long period of time you're interested in. All right, so let's do simple is good then. Let's imagine the case here where we have a few number of sampling dates. And I want to be clear that I'm going to post the link to the website from which I drew this talk. This is a talk built from materials provided for instructors from nature.com, which is the Nature journal, which is a leading journal of scientific studies. And it's a really useful tool, but I don't want to pretend like I made this up. Okay, so I am drawing a lot of information. If you go to that website, you'll see a lot of these same images, and that's by design. I'm trying to follow it as closely as possible so that if you are interested, you can go back and look at it. Now, one of the problems we do have is, let's imagine that we want to measure the y, the height in that case. Well, if we have height at two different time periods, right, we're going to have two different densities. So if you imagine, let's look at that visually. So, I better use this different color. If we went between, let's say, here in the 6 and the 7, if I take the height here, right, the height from the x-axis to this first point over here is different than the height here. It must be lower. So that's not a rectangle, right? That's going to create all sorts of weird shapes for us. And we don't want to do that. I'm going to have some triangles in there and some rectangles. That's not what we're going to do. We're going to do simpler. What we're going to do is say, okay, the height will be the average between these. So we're going to take the height here, and we're going to assume that the rectangle, and let me draw the rectangle on there, is actually this high. Oh my gosh, you can see how terrible my rectangle is. Okay, which means that it overestimates at the one part, right? There's too much over here, and it underestimates at this part. It doesn't incorporate that material. But on average, again, it's going to be really, really, really close, right? And we assume that right at the halfway point is going to be pretty similar to overestimate, underestimate will be pretty close together. So what we're going to refer to in the following calculations is n between time periods. Okay, so we're going to measure density at time 6 and density at time 7, and we're going to assume that the density of individuals at time 6.5 is exactly halfway between those points. So take a look at this now, and I just want to show you this because it's the example that's posted on the website that I'll link. And it's a dragonfly, which is cool. So these are nymphs living in a stream. And what you can see is how many there start out with in May. So at the beginning of the growing season, you can see it's almost 300 animals per meter squared. That's a lot of dragonfly. But look, by the time you get back around to March, right, the density is down to 16. So an enormous number of these animals are not going to be there when we get back around to the following year. And the reasons for that are going to be simple. Either they could have been eaten, they could have died, I should say either they could have died, probably by being eaten, or to a disease, or they could have literally left the system, probably from something like drift. But in any case, they're not there anymore. Conversely, look at the weight. Look how small they start, 0.076 milligrams. That's so tiny, a milligram, right? You try to look at a nutrient label and see how many milligrams are in something, right? In a single serving, which is often hundreds of grams, you have thousands and thousands of milligrams, right? So 0.076, this isn't even 1 milligram. This is a tiny little speck of a dragonfly. Conversely, by the time you get down here, this is a pretty reasonable sized organism. You'd have no problem finding this just with your eye. 27 milligrams is a reasonably large organism. Not a huge organism. Okay, this is not an elephant walking around, but it's a large organism. And look, you went up 3 orders of magnitude here. 4 orders of magnitude, right? Because you started at 0.76 and you have moved that decimal, so to speak, forward that many places, right? You end up over here. That's a huge shift in the weight. Think about how that difference that is causing. So if we plot all those points, this is what we get. The black dots here and the gray line is a number of individuals per meter squared. So it's this axis over here. The red dots are the weight of those individuals through time. And look, you get that nice sort of leveling off. And that's posted over here on the red axis. Okay, and I put the picture up here because I'm an ecologist and I can't help myself. So there's a period of very rapid growth, which is in sort of here, right? And then there's a period of leveling off, which is this area here. And for the first part of this, by and large, there's not much change in the total weight of the system because the animals are small and they have to get a lot bigger before their weight drastically increases. So it takes a little while before they get started. Also, what's going on here, right? It looks like we actually made organisms. So if you ever do sampling in a stream, just be aware, variability exists. It is very possible that this point was undersampled, but it looks so much in line with all the other points that I suspect what's actually happening here is that a large number of organisms were brought into the system by, say, a large rain event, which washed a bunch of smaller animals from upstream into that system. And so change the total numbers. You can see very rapidly, right, that those animals were not supported in that system. So either they died or they left almost immediately after that. But it so happened at that one event that they were very high. Now this would be another great SMP project if you're thinking about stuff like this, is to pick some species and then do this through time. Just look at it, see how much it produces in a system, or compare it for a couple of closely related species in a system, right? does one dominate when we think about production, and one is less abundant, right? How fast do they go? And this can be done very easily with relatively few tools. It'd be a really nice, simple undergraduate project. Okay, I'm just pointing out that point. So you could you can put these into a cute little table like I've done here. I'm showing you how to do this because I anticipate that this is what I want you to be able to do. And what I want to show you is that it's very, very simple. What you do is you put the number of animals in one column, the weight of those animals, or the average weight of those animals at that time in another column, and then you subtract the weight at time 2 from the weight at time 1, and that's what the change in weight is. So that's how much weight they changed in that time. Okay? And you could do that all the way down, right? The first one will not have a weight change. It was sampled at that time. There is no sample at time 0. So if we move forward, you can just drag that down if you're in Excel, right? And you'll see, again, this value here is built from this value minus that value. And the same, it goes all the way up like that, okay? You can do exactly the same thing, or I should say, what you're going to do now is take the average of the densities to get this next column, which is called n bar. All right, that's value. So you can see that the average of 279 and 172 is 225. And the average of, I'm going to try to do this to prevent confusion with a bunch of lines, 43 and 16 is 29. Okay, and you can do that all the way through. Again, the first one doesn't have a corresponding partner, so it doesn't get measured. And now all you have to do to calculate production is multiply those two columns together, and they will equal the next column. So 0.268 times 225.5 will get you the amount of production in milligrams per meter squared, right? Because we have animals per meter squared. So this is number of milligrams per meter squared of this species of dragonfly in your stream. And you can add that up at the bottom, so the entire column, and get the total amount of production of this dragonfly in a year, in a full year of growth. So in every meter of squared of stream bottom, you're getting about, what, 2-ish grams of dragonfly. That's cool. If you got 2 grams of dragonflies are predatory. There's got to be a lot of biomass to support that, right? There's got to be tens of grams of other biomass out there for them to be eating. So now you're starting to understand how these systems are linked together. So that's the total annual secondary production there. And you can plot that. Here the completely black circles are now the production. So this is the production per unit time, and I've plotted them between, right? So they don't align right with it. Oh my gosh, I'm sorry. They land right between these points because that's where they're being estimated. And you can see that what I'm actually doing is estimating this total area underneath here, right? All this if you want the annual. That's what we're adding up for all the annual stuff, which is really, really neat. And you can see that it goes up at one point, then it comes down and maybe goes up again, and then it really drops off as they get larger. Your production per unit is very, very small from here to here because the difference there's not much difference, right? The weight of the organism is relatively similar. All right, so why do we care about this? Well, you can start to estimate things like the efficiency of a system. You can estimate things like the limits of energy available. You can start to draw these really intricate food webs where you actually can define how much energy is flowing to each different group, right? Really neat stuff. We're not just talking about, well, dragonflies eat a lot of other stuff, but I'm actually quantifying how much of something else these dragonflies are eating. I can tell you, yeah, these dragonflies consume 15% of the biomass of caddisflies that are produced in your stream. Think about that, right? That's an interesting and far more informative way to think about it. In addition to that, because we're boiling these species down to numbers, we can actually think about comparing species one-to-one. When I just compare a dragonfly to a dragonfly, you might say, well, that's pretty similar, apple to an apple. But they're a lot different in size and they emerge at different times. Maybe they are important in their own ways. But let's actually look at how much energy each one uses. Wow, this one uses 1,000, or let's say it makes 1,000 grams per meter. I know I'm being a little extreme. 1,000 grams per meter squared of stream bottom. And this one makes 1/10 of 1 gram per meter squared of stream bottom. This 1,000-gram one must be really important to the system. This 1/10 appears not to be as important. Why is that? Right? Maybe we could ask that question. Would it be more important if we remove the other one? Right? There's all sorts of interesting ways in which you can think about asking deeper questions once you know that. So this converting of an animal into a number, and that's kind of what I want you to think about, allows us to ask even more informative, more intelligent, more interesting questions about these systems. I know at this point, I'm sure that many of you are rolling your eyes. I also want to remind you, this is a good time to do so, that again, that all models are wrong. This is a simplified version of a food web. It's a simplified version of thinking of a species, or again, you could combine all the species at a trophic level and think about it this way. But we have to understand this very complex world through simplified means. We simply cannot look at it and just intuit information from it. You have to break it into much smaller and simpler pieces for our mind to comprehend. And that's what this approach does, right? So we're going to actually go through one more modeling approach in the next lecture, which is called size spectra analysis. And it's another way to look at food webs because, again, there are many, many ways we can look at food webs. Each one of these has different advantages and disadvantages. I chose size spectra because it deals with trophic levels and transfer efficiency again. So it'll be, you'll look at some of the same sort of patterns we saw here. Right, so next up will be that lecture.